In this video, I'll be discussing entropy. Entropy is a state function of thermodynamics symbolized by the letter S, and it's the measurement of disorder in a chemical system. And that's based on this notion that at 0 Kelvin, absolute zero, enthalpy is zero. Because at that point, there is no movement to generate disorder. And all entropy values for chemical systems are based on this notion that at 0 Kelvin, entropy is zero. This is the third law of thermodynamics. For states of matter, gases have a higher entropy and solids have a lower entropy. And that's because gases are more free-flowing, they're more fluid, and gas molecules are far more spaced out. Whereas solids are more crystalline, they're more compact, they're more structured, and they're more organized. Therefore, they have a lower amount of disorder, therefore they have a lower entropy compared to gases. In general, you're going to see an increase in entropy whenever you go from a more organized system to a less organized system. Because remember, an increase in entropy means an increase in disorder. So melting is where you go from a solid to a liquid, and that is going to increase your entropy because you're going from a more organized system to a less organized system. Vaporization is going from a liquid to a gas, and that's also going from a system that's more organized to a system that's less organized. It increases the entropy. Sublimation is going from a solid to a gas, and the same thing applies. You're increasing the disorder, therefore you're increasing the entropy. When you have a reaction that forms more gas molecules than you started with, that increases the entropy because you're generating more gas molecules. More gas molecules means a higher amount of disorder, therefore a higher entropy. When there's a dissolution of a salt into its ions, that increases the entropy because you're taking a solid salt and you're breaking it apart into ions, therefore increasing the disorder. So here's some chemical reaction examples of entropy changes. So in this first example here, we have solid water changing into liquid water. So we're going from a more organized system to a less organized system. Therefore, the change in entropy is greater than zero because we are increasing the entropy of this system. In the second example here, we have two NO2 molecules forming one N2O4 molecule. So we're taking two gas molecules and we're fusing them to make one gas molecule. So because we're going from more disorder to less disorder, our entropy is decreasing. Therefore, we have a negative entropy value here. Delta S is less than zero because we're decreasing the entropy of this system. And our last example down here, we have solid sodium chloride, salt, dissociating into sodium ions and chloride ions. And again, this is a dissolution of a salt. We're going from a solid to ions. Therefore, we're increasing the disorder, so our entropy is greater than zero. We also are going to have an equation down here where we can solve for the entropy of a chemical reaction. And it's going to be the same basic setup that we saw with enthalpy when we saw the standard enthalpies of formation. There is also a set of standard entropy values that we can use to calculate entropies of reactions. So let's go ahead and look at an example of that now. So let's look at this example here. So we have this reaction where tungsten oxide is reacted with hydrogen gas to produce solid tungsten and water vapor. And the question asks us to calculate the change in entropy for the reaction below, given the standard entropy values listed over here in this table. So two things I would like to point out to you. One of those things is that elements in their natural form have an entropy value. When we talk about enthalpy, we said that elements in their natural form don't have an enthalpy. Well, they have an entropy, so make sure you keep that in mind. Another thing to keep in mind is the units for entropy. You have joules per mole Kelvin, and that's the unit you'll often find when you look these numbers up in the tables that you find online. This is how the units are almost always listed for entropy. For enthalpy, and later you'll talk about Gibbs free energy, their units are almost always listed as kilojoules per mole. So definitely keep in mind that your units are different for entropy. So if we want to set this up into our equation, we need to look at the products first. So we have solid tungsten, and there's only one of those on the product side. So we have our entropy value for solid tungsten as 32.68. Plus 3 times the entropy for water vapor, because we have 3 water molecules here. So water vapor is 188.72. And you're always going to want to multiply these values by the number of molecules you have in your reaction based on that coefficient out front. And we're going to take this value and subtract it from the sum of the reactants. So our reactants are tungsten oxide. There's only one of those. And the value for that is 75.89. And we have hydrogen gas, and we have 3 of those. So we're going to have 3 times 130.59. Okay. So let's go ahead and do this math and see what we get for our value of delta S. So if you do your math, you should get your delta S equal to 131.18 joules per mole Kelvin, which makes sense. Our delta S is positive, therefore our disorder increased for our reaction. So one last thing to keep in mind for your delta S values, you can use them alongside your delta H values for a reaction to judge its spontaneity. So ultimately, when you learn about Gibbs free energy, you'll learn very quickly how to determine if a reaction is spontaneous or not. But for right now, you have 2 state functions you can deal with. You have enthalpy and entropy. And you can use the values for both of those to determine if your reaction is always spontaneous or always non-spontaneous. So if your delta H is less than 0 and your delta S is greater than 0, your reaction is always going to be spontaneous. And for the opposite, if your delta H is greater than 0 and your delta S is less than 0, your reaction is always non-spontaneous. But like I said, when you get to Gibbs free energy, you'll learn a very quick way to determine if the reaction is spontaneous or not based on the value for delta G. But for right now, you can use delta H and delta S to judge spontaneity.